So let's talk about quadric surfaces. Now, what's a quadric surface? It's described by an equation of this form, okay? So here you have the highest power being 2 of different variables. So x squared, y squared, z squared. Or you could have an xy, xz, yz, an x, y, z, and then just a good old-fashioned uh, constant. A, b through j are just constants. So any surface that could be described by this equation is called a quadric surface. So let's take a specific example. Let's look at a specific example here. So consider the function of three variables, and we'll talk more in depth about functions of two variables and three variables. But for now, just consider it something that we could give three different values to, and it returns given a certain value. Okay, so here we have an x, y, and z that we could give this function, and it will return to us this number here for our given x, y, and z. And we are told to describe the mathematical object f, x, y, z is equal to 0. Okay. Now, whenever you take a function of three variables and you set it equal to a constant, in general, what that's called is a level surface. What you get as a result is a level surface. And we could see why, because look at f, x, y, z equal to 0. Let's take this expression, put it in here, and we get this over here. Now, what is that? Well, that's going to be, if we could move this one to the other side, and we have ourselves a quadric surface, okay? So this is a quadric surface. A here, for example, would be 1/9 because of this 3 squared. I kept them squared for a reason, just to make things clearer, but you could definitely just consider that 9, 16, and 25. So yeah, this fits the bill. For us, j is equal to -1, and a, b, and c are given by 1/9, 1/16, 1/25 respectively, and we have then a quadric surface. Okay, now you see this thing and you wonder, well, how does it look? Okay, so just to recap real quick, you get a level surface by setting a function of three variables equal to some constant, and it happens to be that that level surface for us is a quadric surface, and we are now left with this relation. Whenever you see an equation like this, what you're really thinking about is a set. Okay, this is basically the set of points x, y, z such that you respect that relation. Okay, so for example, would the point 0, 0, 0 be in the set? Well, we could plug 0 for x, we could plug 0 for y, and we could plug 0 for z, and so we'd have on the left hand side 0. 0 does not equal 1, so 0, 0, 0 is not in this set that respects this relation. Okay, so what's the strategy to finding out how things like this actually look? Well, one strategy we could take at the beginning is to find out where this object here intersects the different axes. Okay, for example, let's take the z-axis. Well, what describes the z-axis? The z-axis, you'll be along the z-axis whenever x and y are equal to 0. So if x and y are equal to 0, then you know you're on the z-axis. So let's plug for x 0 and let's plug for y 0, and we get this solution for that. Z is equal to plus or minus 5. What does that mean? That means the intersection of the set of points that respect this relation that you see there, and they are also on the z-axis, are the points plus or minus 5. So far we have the point 5 and minus 5 along the z-axis. Those 2 points are part of our relation here that are on the z-axis. So along the z-axis, this object, whatever it is, intersects at 5 and minus 5. So we could then look at the x-axis. All right, and how do you describe the x-axis? That's where y and z are 0. And doing the same thing, you'll get plus or minus 3. So we know that our object intersects the x-axis at plus and minus 3, and the y-axis, then we know that our object, that these 2 points here, this is 2 points because of the plus and minus, so both the plus and minus are, you know, they respect the relation fx yz equals 0. And I wrote this in 3 different ways. So I wrote here, thus these 2 points are in the set. Okay, so here I'm thinking about it in terms of a set. Okay, and here I'm thinking about it in terms of a surface. You know, I may say all 3 of these things. Here I just call it a relation, but this is all saying the same thing. So these 6 points that you see here, what are they? They are in this set here, the set that respects this relation, and also along the different axes. Okay, so what's the next thing that we could do to get a better grounding of what this thing is? How about we look at slices of this object? Okay, and what do I mean by slices? Here, the kind of formal way to say this is to call it a trace. And let's consider fixing z equal to some constant z naught. Z naught is in R, okay? If you want to take an example, you could take z naught equal to 2, all right? But let's think now of z being equal to some constant z naught. Okay, so we're not playing around with that. We're not changing it. Then we could solve for, you know, we could then, since we're considering this z a constant, let's move it to the other side. And we get this relation here, okay? This may remind you of something, the left-hand side. Reminds you of ellipses, right? And you would not be wrong for that. So here I take a concrete example of z naught equal to 2. Then 1 minus 2 squared over 5 squared is going to be 21 over 25. And so we have this thing here, okay? Now this is an ellipse. What you're seeing here is an ellipse. We could multiply this 25 to bring it here and divide by 21 and just get 1 there. So it gives us a formal ellipse. And this object here, what you're seeing now, this object here, what is that? It's the intersection of the set that respects the relation above and the set z is equal to 2. What is that set z equal to 2? That's a simple plane, okay? This is a simple plane that that's at z equals 2. So it looks like it's parallel to the xy plane, but at z equals 2. Okay, you could think about it as being this plane up here. Okay, and now what you're seeing here in blue, this guy here, that's this. Okay, it is the intersection of the z equal to 2 plane and our object. All right, so our object intersects at these different xy's when z equals 2. And another way of saying that is I could take this over here, just this left hand side, and create a new function gxy and set it equal to this left hand side, and then this ellipse, this blue ellipse which I draw on the xy plane. What happens when you take a function of 2 variables and set it equal to a constant? You don't get a level surface, but you get a level curve. Okay. Why are you getting a level curve instead of a surface? Because imagine you choose an x, just fix x to something, then y is determined. So you only have 1 degree of freedom in a sense, that once you choose one of these, then the other is determined. On the other hand, when we had this object here, I can choose some z, but x and y are still free. I would have to choose two things, say y and z, and then I could solve for x. So you have to choose, say, x and y, and then solve for z, or y and x, or y and z, and then solve for x. So here you have 2 degrees of freedom, and so something with 2 degrees of freedom is going to be a surface, right? On a surface, you could move left, or you could move up and down, right? Right and left, or up and down. So you have 2 degrees of freedom, whereas on a curve, there's really just a one-way street, right? It's left or right. You can't move up and down on a curve, and that's a reflection of the fact that we only have 1 degree of freedom in the sense of one free choice. Once we make that one free choice, the other variable is determined. Okay, so that's the idea of level curves and surfaces. I just kind of wanted to introduce it from now because we run into this a few times in the semester, and I just thought to get it out there at the beginning. You'll be dealing with this concept later in the future as well. So what is the level curve of the function gxy when you set it equal to the constant 21 over 25? You get this guy here, which if we plot this on the xy plane, this is now just a relation of x and y. We get this blue ellipse that you're seeing over there. And what the heck is that? Well, that's where the z equal 2 plane intersects this general shape of ours, okay, this relation here. And so you're getting this slice. This is a slice, also called a trace. We didn't have to choose z equals 2. We could have chosen z naught equals 0. If we choose z naught equals 0, what are we going to get? We're going to get x squared over 3 squared plus y squared over 4 squared equals 1, because z naught would be equal to 0. And then you'll get an ellipse with a semi-minor axis of 3 and semi-major axis of 4. You'll get this green curve, okay? And it lives in the xy plane, all right? So sometimes we draw these above the xy plane, but really they're all living in the xy plane. We had reduced z to some constant, but for visualization, we intersect it, we intersect the plane and the graph together just for visualization. So that's where you get this green ellipse. And what is that green ellipse? That's the intersection that you would get when you intersect the z equals 0 plane with our general shape. Well, we don't have to stick to just simple planes with z equal to a constant. We could set y equal to a constant. Let's try to do that. Let's go back up to our shape, and we set this time y equal to a constant. When we do that, what do we get when we set y equal to a constant? Well, we'll have x squared over 3 squared plus, let's choose the constant y equals 0. So 0 squared over 4 squared plus z squared. We're not fixing z to anything. Now we're just fixing y to 0. All over 5 squared is equal to 1. So this guy here is just 0, and you get this x squared over 3 squared plus z squared over 5 squared equals 1. What is that? That is an ellipse also. Okay? It's an ellipse with semi-major axis 5, semi-minor axis 3, but in the x and critically here, z plane. I drew it with the z plane. And where does this shape show up along our curve? It shows up here. That's what you would get if you intersected the y equals 2 plane. Okay. Here's the, sorry, not y equals 2, but y equals 0 plane. So here's the y equals 0 plane. And if you intersect it with the with our shape, then you end up getting this red ellipse that's on the xz plane. Okay, we could now keep checking the different slices, and we would get, for example, if we went down to z equals -2, we'll get something similar. Okay, and we could also continue along, say, y, and we realize then as we increase y, the ellipses get smaller. In past z equals 5, in past y equals 4, then no point respects that, right? If z is greater than 5, let's take a look. So if z was greater than 5 here, then this ratio would be greater than 1, which, you know, that's impossible. So even if x and y were 0, if z is greater than 5, there's no way you could get some point that will cause you to be equal to 1. Okay, if x and y are being squared, you can't subtract anything from that. So we know nothing exists beyond z equals 5 or less than z equals -5. Nothing exists beyond x equals 4 or sorry, not x equals 4, but x equals 3 and lower than x equal -3. And what this shape is at the end is called an ellipsoid. Okay, it's a 3D ellipse basically. If we erase all of this, let's erase it. So if you kept filling them in, and then the last part is to connect all of these different traces together, you'll see that you have this, for lack of a better word, egg. Okay, it looks like an egg. It's an ellipsoid. But hopefully, you know, you're thinking a little more about sets and how this works, and understanding what happens when you fix certain variables, understanding what happens when you set functions equal to constants, and learning how to visualize relations in terms of x, y, and z as shapes.